Let's discuss the problems from tutorial 5. Now in 8051, the looping action with instruction dj and z is limited to how many iterations. So what does this dj and z instruction do? Well, it decrements the contents of this register x, and when x is not equal to 0, it jumps over to this relative address. So here you need to note that the relative addresses, this is a 3-byte instruction, and our relative address is 1 byte long, or 8 bits. So this means that we can only specify a maximum of 2 to the power of 8 or 256 possible addresses. So in this case, if you are to use dj and z as a looping mechanism, you would be limited to 256 iterations. Moving on. So what's the advantage of short jump over long jump? So both these instructions allow the program flow to change. Now the difference between the two is that the short jump uses 1 byte of address space, whereas for the long jump it uses 2 bytes in address space. So essentially, if you have a jump which is not going to be more than, again, any location which is going to be more than 256 bytes long, then a short jump would be better, because when this instruction is encoded, a short jump requires 2 bytes of code memory, whereas a long jump is encoded in 3 bytes. So the advantage is your short jump uses less ROM space. So find the number of times the following loop is performed. Okay, let's start with initializing R6 with the value 200. Note this 200 is in decimal. Then here we have R5 getting assigned the value 100. So this instruction tells us to decrement R5 and keep looping until it reaches 0. So we decrement R5, this becomes 99 now, and since 99 is not equal to 0, we jump back to here. Again decrement, not equal to 0, jump back to here. So this is going to loop 100 times until it reaches 0, at which point it exits. Next, in this instruction, we see that we have to decrement R6 by 1. So R6 now becomes 199, and since this is not equal to 0, we loop to jump. We jump to this instruction located at memory location back. So again here, let me just make this space bigger. So we reinitialize R5 to 100, come back to this inner loop, which again takes it through 100 iterations, and once that's done, we move back to the outer loop, which decrements this by 1, and then we come back to the inner loop. So essentially you will find that the outer loop iterates 200 times, and for each iteration of the outer loop, the inner loop iterates 100 times. So therefore this particular instruction is going to be, this two loops will iterate for a total of 200 by 100, which is for 20,000 times. So write a program to load the accumulator with the value 55H and complement the accumulator 800 times. So here we have to realize that the limitations of using short jump is that you can only do 256 iterations. So therefore, to achieve 800 iterations, we need to nest two loops together. So let's start by moving the number 55 in hexadecimal over to the accumulator. So note I'm going to use the immediate value, therefore I need to precede it with 55, and H symbolizes this is hexadecimal. So once this is done, we would need to initialize our loop counters. So let's store the loop counters in, say, register R0. So to get this loop to iterate over 800 times, I can choose two loops. The outer loop can go 10 times and the inner loop can iterate for 80 times. So initialize R0 to 10. This is my outer loop, and then we can initialize R1 to 80, and note I'm using decimals. Right. So after this is done, what we can do is we simply complement the accumulator, and decrement R1 and keep looping. So I'll define, let's say, my inner loop at this line. So I would keep looping until R1 becomes 0. So this is our inner loop, and once this is done, we need to set our outer loop here. So R0, decrement R0 and keep looping until it becomes 0, and the place to jump would be the outer loop, which is here. So this defines the outer loop. Okay, so as you can see, what ends up happening is we will have 10 iterations of the outer loop, and within each iteration of an outer loop we will loop 80 times in the inner loop. So this would bring the total number of iterations to 800 times. The target address of a jump backward is a maximum of how many bytes? So when you consider jumps, the jumps are essentially relative addresses with respect to your program counter. So forward jumps are jumps in the positive direction and backward jumps are jumps in the negative direction with respect to the program counter. So if you consider that our short jumps are limited to 8 bits of relative address, this 8 bits has 2 to the power of 8 possibilities or 256 possibilities, and when we express them, so this is 0 0 0 all the way to 1 1 1 1 1 1 1 1, and so you will find that if you consider these 8 bits as a signed number, then you have 127 values which are positive and 128 values which are negative. So given the fact that when you consider a short jump, you are essentially specifying a relative address with respect to the program counter. To do a backward jump, you can have a maximum of 128 bytes, whereas to do a forward jump you would be limited to 127 bytes. Compare and contrast LCALL and ACALL. So LCALL stands for long call, and this is a 3-byte instruction in your code memory, whereas the ACALL stands for absolute call, and it consumes 2 bytes in your code memory. So one of the fundamental differences between the two calls is that of the 3 bytes, the 2 bytes are used for to express the address. So 2 bytes means 16 bits, and therefore you can access a total of 64K memory space. On the other hand, so let me just complete this. On the other hand, in case of the absolute call, the 11 bits of this total 16-bit is used for expressing the memory address. So after the opcode, the 11 bits express the memory address. Therefore you can address a maximum of 2K memory locations with ACALL. So these are the differences between the two. Now, is there any similarity? So both ACALL and LCALL are subroutine calls, and being subroutine calls, what happens is both of them will require the stack to store the program counter. Now remember, our program counter is 16 bits wide, and therefore it requires 2 bytes of storage space in our stack. The lower bits of the return address go first, and then followed by the upper bits. So this is the lower bits of the return address, and these are the upper bits of the return address. So regardless of whether you have ACALL or LCALL, both of them will consume 2 bytes of memory in your stack. Why do the push and the pop instructions in a subroutine need to be equal in number? Well, the reason for that is quite simple. When you consider what happens when a subroutine is called, you'll find that the calling function the LCALL or ACALL for that matter, they save 2 bytes of the return address on the stack. So this is return address, the lower bits, and this is the upper bits of the return address, the lower 8 bits, and this is the upper 8 bits. So if the subroutine is going to make use of the stack and push some values, say 3, 5, 8, whatever, and if you have fewer number of pops than what has been pushed, what ends up happening is you will be returning to the incorrect address. And of course the same applies if you have more pops. If you have more pops than pushes, you would end up removing the return address from the stack, and your program code returns to whatever the stack pointer ends up pointing to. So both these conditions are undesirable, because after your subroutine finishes, you are not going to go back to the original calling function. So this is very important, that you ensure that your pop and push instructions are equally matched. So a student learning to write subroutines in an assembler has written the following code. And the multiply or mult subroutine takes 2 parameters passed onto the stack and multiplies them. The low order bits of the results are returned to the main function. So other than the fact that this program really doesn't do much, you could have just written a single line of code which is to multiply A and B and get the same thing done. Other than that, let's trace this program and see how the stacks operate, and how is it that the student managed to get the correct answer even though the approach is totally incorrect. So let's start with this main program. We have a couple of registers. R2 is initialized to 0, and then what we are doing is going to push this onto the stack. So here is our stack, and let's have a stack pointer. So suppose the stack pointer starts off at location 7. Here's 7, 8, 9, etc. So note your push is pre-increment, so we increment the stack pointer and then push the value onto the stack. So now at memory location 8, the value 0 is stored. We then put 0b in R2. This is at this instruction, and we then push the contents of R2 onto the stack. So we increment the stack pointer, and now memory location 9 will hold the value 0b. Then at this line what happens is we are calling the mult subroutine. So in preparation for this call, what would happen is we need to save the return address onto the stack so that we resume the execution of the program once the subroutine finishes. The return address is this memory location here. So we will first save onto the stack, increment it to 10, the lower bits of this address here, which is 0b, and then increment the stack pointer, store the next byte, which is 00 hex. So this is our return address, and these two are the parameters which are passed to the subroutine. So at this stage, after this function call has been made, once we have saved the return address, the flow of program is going to change over to this memory location. So essentially the way that is done is the program counter changes from, so the program counter would have been at 008, the program counter changes to 0011. So we are now at this instruction. We clear the carry bit, then pop into register 2. So pop is going to take the top of the stack here and place the results in register 2. Pop happens to be post decrement, so once pop is done, the stack pointer changes to 10. So essentially there is no value here. Well, actually the value 00 stays there, but we are just deciding that it's not there. Move R2 to the accumulator A. So now the accumulator is initialized to 0 in hex. We pop again once more into R2. So R2 is going to hold 0 B H, and the stack pointer now changes to 9. So this is the current stack pointer. We multiply A and B. So we copy the contents of R2 into register B. So this makes it 0BH, and then we multiply A and B. The result is of course 0. So you will have 0 here as well as 0 in B. This is 00H. And then we are required to move A into R3. So there is some register called R3 which will now have the value 00H, and we simply push 00 back onto the stack. So push is pre-increment, so make it 10. The current pointer is here, so this becomes 00 on the stack. Once we have pushed, the next instruction is to return. So what happens in return? Return is going to pop the 2 bytes on the stack into the program counter. So now our program counter becomes 0000B in hexadecimal. So the program now returns to 000B, which is here. We pop, so let's not forget to decrement the stack pointer. So then we pop into R7. Value goes the stored value is 0. Stack pointer now goes back to being at 7, and we move 0 0 into accumulator. So this becomes the final answer, which is 0 0 in H. And then we come to this instruction, which essentially puts the microprocessor in an infinite loop. Okay, so what you can see from this piece of code here is that the student may be happy that they got the right answer and the program returned to the correct location, but you will find that the student was just simply lucky to have this done. The error here is that the student should realize that the parameters that are passed to a subroutine are placed lower than the return address. So when you are reading the data of your stack, you need to ensure that you ignore the immediate first 2 bytes, which are the return address, and then you will encounter your parameters which have been passed. So in this case, things worked out because the student was extremely lucky. In worst case scenario, what would have happened is the return address could have been completely incorrect, and the program flow would jump to some other region of memory which might just have garbage in it. The next question is to write a function which takes 2 arguments and returns the smaller of the 2 arguments. So the point here to realize is that 8051 does not afford us with any relational operators that allow us to compare different numbers. So what we have to do is to rely on the existing arithmetic and logical operations to implement these relational operations. So one way we can do this is to, let's say, subtract x from y, these two x and y being the arguments. If we subtract x from y, and if the result is negative, well, that tells me that x was less than y. And if it's a positive value or 0, for instance, then it simply implies that x was greater than or equal to y. So we can make use of this simple identities to write our program. So this is the code I wrote. It's a simple function. It receives the 2 arguments via register 3 and register 4, and it returns the smaller of the 2 via the accumulator. So the code begins by looking at, let's put some values and see for ourselves how this function works. Suppose R3 is 5 and R4 is let's say 7. So what happens here, the accumulator will have the value 5. We clear the carry bit, subtract the contents of accumulator with R4, so 5 minus 7, that will be a minus 2. Now what this instruction does is it jumps when a particular bit is set. So we look at the accumulator. The accumulator has 8 bits, and what this acc.7 tells us is for us to test the most significant bit in the accumulator. And the reason for that is you'll find that signed numbers will have the most significant bit set to 1 if it is a negative integer. So what this condition does is it tests for the most significant bit to see if indeed it is a negative value. If so, the program jumps to found location, and here we update the contents of A with R3, which is 5. So the function returns with 5 as being the smaller of the two. Let's reverse this. Let's say if in case R3 was 7 and R4 was 5, what happens then? So here's my accumulator. We copy R3 into A. So now A has 7. Clear the carry bit. Subtract 5 from 7. So the result is going to be 2. The jump bit in this case, if you look at the most significant bit, will be a 0. In fact, this will be the value that is stored in the accumulator. This is the binary equivalent of 2, and you will find the most significant bit is a 0. So since this particular bit is not set, it will move on to the next instruction, which simply puts R4 into the accumulator, and we jump to exit, which returns from this program. So in both the cases, it doesn't matter whether the order in which you pass the parameters, the program correctly returns the right value, which is the smaller of the two arguments. For the last question, we are required to write a program which compares two 8-bit numbers bit by bit. So suppose this is my number 1, and we have another number. So we have to compare it bit by bit, starting from the most significant bit, and report back on the index of the bit where the first mismatch took place. So again, there are many ways of doing this. I can probably give you a hint on how to work on it. You can consider using the XOR operation, which if you have two 8-bit numbers, and when you're doing a bitwise XOR, what this XOR does is it compares the two values, and if they are different, then it gives a 1. If they are the same, it will be 0. So these two bits, when XOR together, look like this. So in our case, the very first mismatch happened at the 7th, the most significant bit, and depending on how you label it, we can call this 7 and we can call this 0. So this is where the program should return the index at which the mismatch took place. So I will leave our discussion here, and I would expect students to post the solution to this problem on the forums.